Hello, welcome to the course SJPHY1C01 Properties of Matter and Thermodynamics. The contents of today's lecture is taken from Heat and Thermodynamics by Brijlal and Subramaniam. We'll continue to discuss topics from Module 3 Thermodynamics. Having familiarized ourselves with the concept of heat and thermal equilibrium, it's time now to move on to first law of thermodynamics, which states that when heat Q is supplied to a system which does external work W in moving from state 1 to state 2, then the amount of heat supplied is equal to the sum of increase in internal energy of the system and the work done by the system. So imagine that you have a system in state 1 characterized by internal energy U1. You are supplying heat Q to the system so that its internal energy increases to U2. Then during the process, the work done by the system is W. So you can write Q equal to the increase in internal energy U2 minus U1 plus W. In other words, a part of the heat energy is used to increase the internal energy and the remaining part is used to do some external work done by the system. Now, the change in heat energy dQ can be written as change in internal energy du plus change in work dW. So basically, first law of thermodynamics talks about the interrelation between heat and mechanical work. So this was first observed by James Prescott Joule in 19th century. He was rotating a paddle wheel underwater, and when he monitored the temperature of the water, he observed that along with the rotation, the temperature is also increasing. So here the mechanical work is converted into heat. Similarly, you can also use heat flow to do some mechanical work, which is the working principle behind any heat engine. So a heat engine consists of a source which is at high temperature and a sink which is at low temperature. So heat flows from source to sink, and during this process, a part of the heat energy is used to do some useful work. Now, when we talk about heat and work, the sign is very important. So by convention, if heat is supplied to a system, it is taken to be a positive, and if heat is removed from the system, the sign is negative. Usually, we analyze things from the perspective of the system. So when you are supplying heat, the system is gaining heat energy, so this is positive. Similarly, if you are removing heat, the system is losing heat, which is negative. The same way, if the work is done by the system, it is considered to be positive work. For example, if some gas is expanding, work is done by the gas. On the other hand, if work is done on the system, it is considered to be negative work. By means of a piston, if you are compressing a gas, you are doing work on the gas. This is the negative work. Now, imagine that you have a system residing in state 1. You are supplying heat energy Q to the system. So, amount of work W is done in moving it from state 1 to state 2. And from the first law of thermodynamics, I can write change in internal energy U2 minus U1 equal to Q minus W. Imagine that you are moving from initial state 1 to final state 2 through different parts A, B and C. Okay. And if you measure the right hand side Q minus W for these three different parts, you will be surprised to see that Q minus W remains the same for all the three different parts. If Q minus W is the same, from this equation, it means that the change in internal energy is also same for the seemingly three different parts. In other words, internal energy is a state function and not a path function. State function means its values depend only on the initial and final states and not the nature of the path taken. This is also true in the case of classical mechanics, where you deal with conservative forces. There you will see that the work done by a conservative force is a state function. It depends only on the initial and final points and not exactly on the path taken. And typically the internal energy can be represented as a function of any of the two thermodynamic variables. So as I said in the previous class, we have three major thermodynamic variables, P, V and T. So you can either define internal energy as a function of P and V, or V and T, or alternatively P and T. For example, if you define internal energy as a function of P and V, then using the partial derivative theorem, I can write change in internal energy du as, first keep the volume constant and take the change in internal energy as a function of pressure. So this is dou u by dou p at constant V multiplied by dP, plus the change in internal energy as a function of volume by keeping pressure constant, dou u by dou V at constant pressure multiplied by d. Same way you can write for other two functions as well. Another important concept is specific heat. Now, heat capacity is defined as the ability to absorb heat to produce a given change in temperature in a given mass. So imagine that you have a material of mass m which absorbs heat Q so that its temperature rises by delta T. Then heat capacity is defined as heat Q divided by change in temperature delta T. You can experience the manifestation of heat capacity in your daily experience. For example, if you are familiar with cooking, you will notice that if you take an iron pan and an earthen pot, keep them on the same stove, the iron pan gets heated up much more quickly compared to an earthen pot. The reason is that an iron pan has a smaller specific heat compared to an earthen pot. So when the specific heat is smaller, it means that for a given heat, the iron pan is going to produce a larger increase in temperature compared to an earthen pot. Or if you take the counter statement, to reach a given temperature, an iron pan is going to take much more lower heat compared to an earthen pot. Okay, so this is the visible manifestation of the heat capacity. Heat capacity is a material property. For different materials, you have different heat capacities. Now, specific heat is related to heat capacity. It is defined as heat capacity per unit mass. So if you take heat capacity Q by delta T, divide it with the mass of the system, then you get specific heat C. So C is defined as Q divided by M into delta T. So you can also define it as the amount of heat required to raise the temperature of a unit mass of a material by 1 degree. Now the unit of specific heat is joule per kilogram per degree Celsius. Now, even though this definition works perfect for solids and liquids, it is ill suited for gases. Now what's the problem with gases? Unlike solids and liquids, gas has a peculiar property known as compressibility. You can compress it, you can expand it or compress it. Now, because of this inherent compressibility, the specific heat values of gases can vary from 0 all the way to infinity. For example, imagine that you have some gas which is compressed adiabatically. So in the case of adiabatic process, the temperature changes but the heat exchange is 0. So if you follow the definition of specific heat, C equal to Q divided by M into delta T, since this is an adiabatic process, the heat exchanged is 0. So your numerator is 0, which gives you the value of specific heat to be 0. On the other hand, if you consider the case of a gas which is expanding isothermally, so in the case of isothermal process, there is a heat exchange but temperature remains the same. Once again, if you follow the definition of specific heat, C equal to Q divided by M into delta T, but delta T, change in temperature, is now 0. So the denominator being 0, you get the value of specific heat as infinity. So there is a huge variation in the value of the specific heat when it comes to gases, which means you need to impose additional constraints. So that's the reason why whenever we talk about specific heat of gases, either we keep the pressure as a constant, this is known as specific heat at constant pressure or Cp, or you specify the value of specific heat under constant volume, which is known as specific heat at constant volume Cv. Now Cp is defined as the amount of heat required to raise temperature of a unit mass of a gas through 1 degree Celsius at constant pressure. So mathematically Cp equal to delta Q divided by delta T at constant pressure. Similarly, Cv is defined as amount of heat required to raise temperature of a unit mass of a gas through 1 degree Celsius at constant volume. So Cv is delta Q divided by delta T at constant volume. So these are two different definitions. Obviously the value of Cp and Cv are going to be different for a gas. Now which one is greater here? So imagine that heat is supplied to a gas and it is allowed to expand at constant pressure. Okay. And the heat supplied is utilized for two things. This we know from the first law of thermodynamics. We know dq equal to du plus dw, or work done, dw you can write in terms of the volume change, dv as pdv. Okay. So a part of the heat energy is used to increase the internal energy, which also results in the increase of temperature, and the remaining part is used to do some useful work. In this case, it's used to expand the gas against the external pressure. Okay. So this is the case of constant pressure. On the other hand, if you look at the constant volume scenario, here the external work done, dw equal to pdv equal to 0, because when the volume is constant, change in volume dv equal to 0, so the work done is 0, which means the entire heat energy is going to be used to increase the internal energy. So if you compare Cp and Cv, in the case of Cv, the entire heat energy supplied is utilized in increasing the temperature, whereas in the case of Cp, only a part of the heat energy is used to increase the temperature, which means to have a change of 1 degree Celsius temperature, you need much less heat in the case of Cv than Cp. Since heat is in the numerator, when the value of heat is less, the value of specific heat is also less. So consequently, the value of Cv is always less than the value of Cp. So Cp or Cp is greater than Cv. One of the applications of first law of thermodynamics is to establish a numerical relation between Cp and Cv. Let's see how do we do that. So as I said, the internal energy U can be specified as a function of any two thermodynamic variables. So let's take V and T. Now I can write U equal to F of V and T. Using the theorem of partial derivatives, I can write change in internal energy du equal to dou U by dou T at constant volume into dt plus dou u by dou v at constant temperature into dv. Now imagine that heat dq is applied to the system, for example some amount of ideal gas, and the volume increases by dv. Then from first law of thermodynamics we know that dq equal to du plus dw, or write dw in terms of change in volume dv, so this is du plus pdv. Substitute for du from this equation. Now I can write dq equal to dou u by dou t at constant volume into dt plus dou u by dou v at constant temperature into dv plus pdv. Now divide both left hand and right hand sides with dt. So dq by dt equal to dou u by dou t at constant volume plus dou u by dou v at constant temperature into dv by dt plus p into dv by dt. dv by dt is common for these two terms, so I take it outside. So inside bracket I have p plus dou u by dou v at constant temperature. Let's now consider the case of constant volume. So imagine that the process is happening, the heat is applied at constant volume. So the left hand side becomes dou q by dou t at constant volume, which we know is Cv. Since the volume is constant, the change in volume dV is going to be 0, which means this term dV by dt equal to 0. So substitute these two into equation number 4. So I get dou q by dou t at constant volume, which is equal to dou u by dou t at constant volume, which is equal to Cv. Now consider the case of constant pressure. So if you are supplying heat energy at constant pressure, then the left hand side becomes dou q by dou t at constant pressure, which is nothing but Cp. Now the equation 4 gets modified as Cp equal to dou u by dou t at constant volume plus P into dou u by dou v at constant temperature into dou v by dou t at constant pressure. Now from the previous equation we know that this term dou u by dou t at constant volume is nothing but Cv. So write Cv here. Now take Cv to the left hand side. Now I have Cp minus Cv equal to P plus dou u by dou v at constant temperature into dou v by dou t at constant pressure. Now we need to simplify this right hand side term. Okay. Now we know that at constant temperature the change in internal energy is 0, because internal energy is a function of temperature. When there is no change in temperature, there is no change in internal energy as well. So this term on the right hand side, dou u by dou v at constant temperature, change in internal energy as a function of volume at constant temperature, is bound to be 0. So I can get rid of this term. Now how do I simplify the remaining term? From the ideal gas equation I know that PV equal to nRT. Imagine that you are taking 1 mole of gas, n equal to 1, so the ideal gas equation becomes PV equal to RT. Now you can take the derivative on either side with respect to temperature. So pressure is a constant, you can take it outside the derivative. So you have derivative of volume with respect to temperature at constant pressure, dou v by dou t at constant pressure. On the right hand side, R is a universal gas constant and the derivative of T with respect to T equal to 1. So on the right hand side you have R. Now using these two results you can simplify equation 5. So equation 5 is Cp minus Cv equal to P into dou v by dou t at constant pressure plus dou u by dou v at constant temperature into dou v by dou t at constant pressure. So this term we have shown as being 0. Dou u by dou v at constant temperature is 0. So this term gets cancelled And this term P into dou V by dou T at constant pressure is nothing but the universal gas constant R. So you get a very simple relation connecting specific heat at constant pressure and specific heat at constant volume, Cp minus Cv equal to R, and this is known as Mayer's formula. So that's for today. In the next class we will discuss about work done during various thermodynamic processes. Thank you.